To help you understand Dart's workflow, these slides begin by depicting a process you should already be familiar with, the numerical integration of a geophysical model. Then they continue by adding in just a couple of additional components to demonstrate how the data assimilation itself is implemented. So, to begin, when integrating a geophysical model, there are typically four components needed: the geophysical model executable, configuration or namelist files that are input to the model that control how the model is run, restart or initial conditions files that store the model state, and scripts and commands that allocate computing resources to run the model and move files around the file system. Since a typical geophysical model needs more than one processor to run, a batch script is submitted instructing the computing cluster to use MPI to run the model executable. After the model integrates forward in time, a netCDF file is output containing the new model state, and the batch job completes. Then a workflow script is invoked to change settings in configuration files and move data files around the file system. Certain modeling systems have their own workflow scripts to handle these tasks for you. For example, CESM and E3SM use the Common Infrastructure for Modeling the Earth, or CIME, scripts to handle the workflow. In this example case, a simple cyclemodel.sh script handles the workflow. It starts by renaming the model output with the date of the integration, year 2025, month 01, day 01, and then sets this newly output file as the input for the next integration cycle by editing the configuration file to reflect that the first cycle has been completed and that rst_2025-0101.nc should be used as the new restart file. With those steps, the first cycle has been completed, and the second cycle is completed much like the first. With the model.in file already configured appropriately, a batch job is submitted that runs an MPI job. The model integrates and a new output file is created. The MPI job completes, and another cycle model script is run that renames the output file with the date of the integration, in this case year 2025, month 01, day 02, and this newly output file is set as the input file for the next integration by editing the model.in file to reflect that a second cycle has been completed and that RST 2025-0102 should be used as the restart file for a subsequent integration. With these four components, we're able to integrate a geophysical model, and adding in two more components enables cycling with data assimilation: Dart programs and observation files. Also, instead of using a single model restart file, Dart uses an ensemble of model restart files. So starting again with our geophysical model, we have an additional executable, which is Dart's filter program, which implements the data assimilation algorithm. Dart has its own configuration file named input.nml, which contains many namelists. And this selection from the filter name list shows that filter reads in multiple restart files, RST 2025-0101, 001, 002, and 003.nc. These are depicted here using slightly different shades of green to reflect the fact that this ensemble contains restart files with slightly different model states, and the assimilation algorithm requires some spread in the ensemble in order for the data to be assimilated. Additionally, a file containing the relevant observations on January 1st, 2025 is needed, and it's stored in a file known as an observation sequence file that specifies the value of the observation and its observational error variance. These files are input into filter, and a batch job is submitted that runs filter using MPI. And after the data has been assimilated, an ensemble of restart files is output by filter containing the new model states after the assimilation has been performed, and then the filter job completes. Since there are now an ensemble of restart files that need to be input into the geophysical model, this workflow now has multiple model.in files that reference each of the restart files in the ensemble. The model.in and restart files are input into the geophysical model, and batch jobs are submitted in turn for each ensemble member, outputting a new restart file after the integration completes. This process repeats for the second ensemble member and the third ensemble member as well. Then a workflow script is invoked to change settings in configuration files and move data files around the file system. Here, the restart and observations files from the first cycle are archived, and the input.nml file is edited to read in the newly created set of restart files. With that, an entire cycle of data assimilation and model integration has been completed, and again, only 2 additional components were added to the workflow to enable data assimilation. The first is the observation sequence file that contains the relevant observations, their locations and error variances, and the second is Dart's filter program that actually performs the assimilation.